So, today, we're going to talk about something pretty radical in the world of AI. Forget everything you know about slow, massive retraining. We're going to dive into how an AI can learn from a single mistake almost instantly using the really elegant logic of geometry. I mean, this is the big one, right? This is the question that's been a huge headache for AI development for years. How do you teach an AI something new without it completely wiping out what it already learned? It's called catastrophic forgetting. Well, it turns out the answer isn't just about more data. It's about shape and space. And the whole learning process kicks off not with some giant data set, but with a single, measurable moment where the AI messes up. The key concept here is something they call surprise. And no, it's not an emotion, it's pure math. When the model predicts one thing, say the word Java, but the correct answer was actually Python, that difference, that gap between expectation and reality, it creates a mathematical vector. It's like a little arrow that points in the exact direction of its own mistake. And what's so cool about this is that it's a completely self-referential system. The model generates its own error signal. It's basically telling itself, okay, this right here is the piece of information I was missing to get that right. This internal signal, that's the raw material for learning.
Okay, but here's the catch. That raw signal? It's a mess. It's this huge, high-dimensional vector that's just swimming in noise. Before it can become a useful memory, it needs to be cleaned up, refined.
And that's where the first layer of memory comes in, the fast memory. You can think of it like a short-term buffer, or maybe a capture net. It's designed to immediately grab that raw, surprise signal the very instant it's created. And it's updating constantly on literally every single token the model processes. So how does it actually clean up that messy signal? Well, it uses a process called projection. It takes that massive, noisy error vector and mathematically squashes it down into a much, much smaller space. And this process is just brilliant because it acts like a filter. It strips away all the random, meaningless noise and leaves behind only the pure, essential signal of the correction. And just how much does it get compressed? This is the part that's pretty mind-blowing. It goes from potentially thousands of dimensions all the way down to just 16. The core discovery here is that almost all meaningful corrections for pretty much any task you can think of, they all live in this one tiny shared space they call the Universal Subspace. Okay, so we've got a pure, clean signal. But how does the system know if this is a real lesson it should learn from and not just some random one-time fluke? Well, that's where the validation process comes in. You know, this step is absolutely crucial. If an AI just learned from every single mistake, it would end up learning from typos or random noise in the data. So the system needs a reliable way to confirm that an error actually represents a stable, repeatable concept worth remembering. And the way it does this is, well, it's just beautiful. It's all geometry. First, it captures that initial 16-dimensional surprise vector, and then it just waits. It waits for other, different surprise vectors that are geometrically similar, which just means they point in roughly the same direction in that 16D space. Once it's collected at least 3 of them, it checks to see if they form a tight cone. If they do, that proves it's a real pattern, not a fluke. The center of that cone, the centroid, becomes the stable, learnable truth. And that number, k equals 3, that's the magic number. It's the minimum threshold. By basically triangulating 3 separate but similar mistakes, the system can be confident that it's not learning from an accident, but from a genuine, real gap in its knowledge. All right, so once a concept is fully validated, it's finally ready to be turned into a permanent skill. It gets stored away in the slow, long-term memory. So a memory in this system has 2 basic parts. It's just like a dictionary lookup. You've got a key, which tells the AI where the problem happened, and you've got a value, which tells it what to do about it. The key is what's called the model's lossless hidden state. And that word lossless is super important. It means it's a perfect, unique snapshot of the exact context. No 2 different situations can ever have the same address. So, for example, fixing Python code on line 47 has a totally different key than fixing Python code on line 89. This precision is what stops memories from accidentally overwriting each other. And the value? Well, that's the triangulated concept we just made. It's now officially called a task coefficient. It's just a tiny little vector of 16 numbers that represents an entire skill or correction. This is what makes the whole system so incredibly efficient. Storing this is over 100 times smaller than trying to save the full model weights. So the AI has all these tiny skills stored away in its long-term memory. Now what? How does it actually use them to change its behavior in real time when it's running? It all comes down to a process called deterministic steering, which is basically defined by this formula right here. In simple terms, it takes the model's current internal thought process, its hidden state, and adds a steering vector to it, physically shifting the model's trajectory towards the correct answer. Let's break that down real quick. First, the current context. That lossless key instantly finds and retrieves the right 16-dimensional skill from memory. Then, a decoder matrix takes that tiny vector and projects it all the way back up to the model's full internal dimension. And finally, this new, full-size correction vector is injected directly into the model's processing flow, steering its next thought. And there's this quote that just nails the idea perfectly. It says, "The memory acts as a lens. It doesn't replace the model's own thinking, it just bends and guides the flow of information to help produce the right outcome." It's a really powerful metaphor. But wait, we're not done yet. There's one final, crucial level to this whole system. We have skills, sure, but we also need something that prevents the model from forgetting, something that lets it learn from the entire history of its mistakes. So this table really pulls it all together. You've got level 1, the fast memory, capturing those raw surprises at super high frequency. Then you have level 2, the slow memory, storing those validated, permanent skills only when they're confirmed. And then there's level 3, momentum. This is a persistent memory that never, ever resets. And this brings us to what might be the coolest distinction of all. Those task coefficients we talked about, those are skills. That's what the model can do. But this momentum vector, that's wisdom. That's what the model knows to avoid. It's a persistent collective history of all its past errors, which allows the model to see a mistake coming down the road and proactively step out of the way before it even happens. So you really have to wonder, if learning is no longer about brute force training on massive data sets, but about the precise geometric correction of self-identified errors, what does that mean for the future of learning itself? It really changes our entire understanding of how an artificial mind can grow, adapt, and even gain something that looks a lot like wisdom.